So in this video, I want to continue working with the same system of nonlinear first-order differential equations over here. And we already looked at this system has two equilibrium. One of them is at -1, 1, and the other one is at 1, -1. So we previously linearized the system at 1 at the other equilibrium, 1, -1, and showed that that was a stable, that was a sinc equilibrium. So let's see what happens for the other equilibrium at -1, 1. And so let's linearize this system again. So we've got our function f of xy is equal to 1 minus x squared. And so if we take the partial with respect to x, we get minus 2x. If we take the partial with respect to y, we get 0. And then if I evaluate this at our equilibrium of -1, 1, so in other words, I plug in -1 for x, that gives me 2. So the linearization for f at this point is 2u, and then we have nothing for the v part. And then let's do the same for the other function, g. Okay, it's already linear, but just to kind of convince ourselves of what we get when we linearize this, the partial with respect to x of g is -3, no matter where we are. The partial of g with respect to y is a constant -3 as well. So then when we linearize g, we get -3u minus 3v. And so now we can write this system as u prime v prime is equal to this matrix of coefficients where we pick the linearization for f over here, and that gave us a 2 and a 0. And then we use this linearization to get the coefficients down here. Okay, and so if you took a look at the previous slide, hopefully you did. This is consistent with if you would have calculated the Jacobian of this system at the point -1, 1, you would get exactly this matrix. So I just wanted to go through it using the linearization way, and some of the other examples we'll just go straight to using the Jacobian. But we're missing a part here. Okay, so that would be the matrix form of that linearized system. And from that, you can find the eigenvalues pretty quickly. You can convince yourself that the eigenvalues for this matrix are a positive 2 and a -3. And since one of these is positive and one of them is negative, that means this is a saddle point, and that's unstable. Okay, there's only a couple of very special directions that would head back towards the equilibrium, but in almost all other directions, actually, if you start off close to the equilibrium, you're going to head away from the equilibrium as time goes on.